Okay, hello everyone. It's my great honor today to introduce our speaker today, Dr. Dibyendu Nandi. Dr. Dibyendu Nandi specializes in understanding the sun's dynamic activity and its influence on our near-Earth space environment and the planetary atmospheres. Dibyendu obtained his PhD from the Indian Institute of Science and subsequently spent 7 years in US working at the Solar Physics Group at Montana State University. Following his return to India, he established the Multi-Institutional Center of Excellence in Space Science India at the Indian Institute of Science, Education and Research, Kolkata, where he is a professor now. Dibyendu has also held visiting positions at Harvard Smithsonian Center for Astrophysics, St. Andrews University, Georgia State University, and the Nordic Institute of Theoretical Physics. Dibyendu's honors include a Parker Lecturership and the 2012 Harvey Prize of the American Astronomical Society, a Vandergrant Visiting Professorship at the Nordic Institute of Theoretical Physics, the 2018 Modeli Award of the Astronomical Society of India, and the 2019 Young Career Award of the Asia-Pacific Solar Physics Society. He is also the Vice President of Commission E4 of the International Astronomical Union and a member of the NASA Israel Heliophysics Working Group and the Indo-US Civil Space Working Group. Let's welcome our speaker again, and Dr. Nandi, you have the seminar now.
All right, thank you, Rizu. So it's a great pleasure to be here when I was invited to give this talk, and there was this weird timing. I kind of was in two minds, but it's a great opportunity to connect with colleagues out on the other side of the world and many of my own students who are scattered over there. Also, Stanford University occupies of space which is very close to our hearts because it operates the Wilcox Solar Observatory, which is one of the prime observatories that provides constraints for solar dynamo models like us. I like to play with the opening slide, and I was trying to look for the logo for COFFIES, and I actually found a cup of coffee. I mean, your logo is a cup of coffee. And so I decided I'm going to stir this cup of coffee and see what comes out of it. So I'm going to stir this now, and this is what comes out of it. So this is how I play, trying to stay awake for the last 1 hour. Okay, just a little bit of context of where we are headed. So we know that the sun's environment, the heliosphere, is a variable environment which is governed by the changing magnetic, radiative, and particulate output of the sun, which manifests as slow, long-term variations in the open flux, cosmic ray modulation, solar wind variations, on top of which transient events like flares and coronal mass ejections cause severe perturbations in near-Earth space. And this image is a reconstruction of density perturbations in the inner heliosphere from the sun to just a few times outside the sun, the Earth's radius. I think this is up to about 4 or 5 AU, based on interplanetary scintillation measurements from the UT Radio telescope in India. And this image, for me, really brings home the point that we live in a dynamic environment, which is governed by a host star, understanding which and predicting whose activity is not only important in the context of protecting our space-based technologies, but this also provides a window to understanding other planetary systems and star-planet interactions in worlds beyond our own. So if you're thinking of predicting the space environment of planetary systems, this is a challenging task, and this I understand to be something that COFFIES is interested in, starting right from the solar interior all the way to sun-Earth interactions. So if you're looking at the sun's interior, we are dealing with a high plasma beta region where the magnetic dynamo operates, creating the solar cycle, and then surface flux transport processes evolve the emerged fields, which appear as sunspots on the solar surface, and create the large-scale surface distribution of fields, which then acts as a lower boundary for the corona and the heliosphere, eventually playing a role in driving both transient phenomena as well as variations in solar radiative output, as well as the solar wind. And then when we go out from the sun's surface out into the atmosphere, we hit the corona, where we are dealing with the region which is a low plasma beta region, where by plasma beta I imply the ratio of the gas pressure to the magnetic pressure, and therefore while the plasma flows really dominate the dynamics of magnetic fields in the sun's interior, out in the tenuous atmosphere, the corona is the other way around, where the magnetic fields govern the dynamics of the plasma. And then when you go out further away into the heliosphere, the solar wind speed increases and the dynamic pressure in the solar wind increases to levels where we are now again in the regime of high plasma beta. And then that stretches all the way out into planetary systems, far out planetary systems like the Earth, where the interactions of stellar magnetized winds and CMEs drive geomagnetic storms and create severe space weather, impacting our space-based technologies as well as some ground-based technologies. I come from a center where our goal is to develop predictive models right from the interior of the sun to studying the impact of stellar winds and CMEs on the Earth's magnetosphere, and we are also now taking this understanding out into other star planet systems. So that's the challenge. You're trying to understand and predict a system which is coupled in physical space, which spans processes which occurs in regimes which are physically very, very different. To give you a sense of what's going on in terms of this challenge, just for solar cycle predictions, if you look at the diversity of predictions for the full solar cycle, for cycle 24, then what you see is that it spans a wide range of amplitudes, starting from pretty much the weakest solar cycles ever observed to the strongest solar cycle ever observed. For context, this dashed line is the amplitude of solar cycle 24. Now, is the situation any different for cycle 25? If you look at, again, the whole zoo of predictions using very, very different kind of techniques, starting from statistical techniques, time series analysis, machine learning algorithms, to dynamo-based or physical model-based forecast, this diversity of techniques yield, again, a very wide range of predictions, which is not too dissimilar from this disagreements that were there in the cycle predictions for cycle 24. So this is where we stand in terms of predictions using a diversity of techniques. But by the end of this talk, I hope to give you an understanding of where we stand in terms of physics-based predictions of sunspot cycle. So what is the context here? I would like to lay down this context so that we appreciate what this field is all about. So when you're able to understand a physical domain or a system or a collection of processes that give rise to a phenomena at a level that is reasonable, you would expect that this understanding would also lead to predictive models or forecasts based on the understanding that will agree with observations. However, this convergence of understanding and physics leading to a consensus or a convergence in forecasts of the solar cycle seems to be still not within grasp of the solar physics community. However, it's important to understand and appreciate that we have made some profound progress in the last decade or so in understanding the predictability of the sunspot cycle. And this will be the primary focus of my talk. And I'll end with a few specific examples focusing on our own work, which has contributed to this understanding and has resulted in a prediction for sunspot cycle 25. An important point to keep in mind, and I think this is an important perspective that people who are from outside the field of solar dynamo theory and are looking at these predictions from a distance, is this. If you look at a similar system, which is the Earth's climate system, the understanding for predicting climate and the development of climate models has progressed over decades and has matured over at least 30, 40 years. However, our efforts to understand the predictability of the solar dynamo mechanism really is barely a decade old, just a little bit more than a decade old. And this really started off somewhere in the late 2000s with the disagreement in two physics-based forecasts for solar cycle 2024, when we started paying very close attention to the physics of predictability. So this is the context I wanted to keep in the back of your mind when you judge the disagreements or the debates and the controversies in the field of solar cycle predictions. So let's take a dive into the interior of the sun. So we know that much of the dynamics in terms of the production of magnetic fields happens in the outer 30% of the sun's interior, which is known as the convection zone, where there exists both large scale and small scale flows, which can in principle feed a mechanism that draws out the energy in these flows and converts this to magnetic fields through a process which we call the solar dynamo mechanism. And because you're dealing with the dynamics of magnetized plasmas here, the field that we use to understand this is based on theories of magnetohydrodynamics. I want to spend a little while trying to give you a sense of the domain that you are dealing with, and particularly for those who are not experts in solar dynamo theory. So one of the governing equations, the most important equation in MHD, that the solution to which will give you the evolution of magnetic field in space and time given some initial condition, and plasma flows and the turbulent diffusivity in the plasma, is known as the magnetic induction equation. This has two terms in the equation. If you ignore the first term, which involves plasma flows, then this equation really reduces to just a diffusion equation, which tells you how the fields will decay and disperse away if the source term, which is the first term, did not exist. Now, if you take the ratio of the first term to the which is the source term, to the dissipative term in this system, you get a number which is known as the magnetic Reynolds number, which is the product of the velocity and length scale of the system divided by the magnetic diffusivity of the system. And typically in astrophysical systems, this number is fairly large because of the large length scales that you encounter. Interestingly, this magnetic Reynolds number also can be simply shown to be the ratio of the diffusion time scales of magnetic fields in the system to the flow time scales. And if you sort of ignore this second term for high magnetic Reynolds number system, you can explicitly invoke a theorem known as Alfvén's theorem of flux freezing, which tells you that in such systems, magnetic fields and plasma flows remain frozen. In other words, if I have a magnetic flux threading a certain surface, which is defined by a certain plasma surface, that flux, as the system dynamically evolves, does not change. This allows plasma flows in a high beta regime where the magnetic the gas pressure dominates the magnetic pressure. This allows the plasma flows to stretch, twist, and induct magnetic fields, thereby providing a mechanism of extracting the energy out in the flows and inducting magnetic fields and sustaining them against dissipation. And this is really, in very simplistic term, how the magnetic dynamo operates in a regime which has high magnetic Reynolds number and also has a high plasma beta. I'll focus on a particular kind of dynamo mechanism, which is known as the alpha omega dynamo mechanism, in which the source terms for the poloidal field are the alpha effect, and the source term for the toroidal field are the omega effect. And I'll describe schematically what is our current understanding of how this dynamo mechanism in the interior of the sun works. So if you have a pre-existing poloidal field, which is a field which is in the r theta plane of the sun, and that's frozen in, and you know that the sun is differentially rotating with the equator rotating faster than the polar regions, then that field which is in the r theta plane will get stretched or inducted into the phi component, which is the magnetic field component in the direction of rotation of the sun. That's called the omega effect, and that produces the toroidal component of the field from the poloidal component. Now, toroidal fields that are produced in the convection zone of the sun, and there are some debates of where exactly it is produced. I will not get into that debate in this talk today. But strong toroidal fields are subject to buoyancy instabilities, and they rise up to the solar surface and form bipolar magnetic sunspot pairs. The sunspot pairs are observed to be tilted. And it is believed that this tilt is imparted by the Coriolis force in rotating systems while the magnetic flux tube is rising radially upwards. And as we will see, the tilt of this bipolar sunspot pairs play a very important role in sustaining the dynamo process by reconverting the toroidal component of the magnetic field to the poloidal component. Of course, there are various mechanisms which have been proposed as a source for the poloidal field, and the emergence of tilted bipolar magnetic regions, or BMR, followed by the surface flux transport process, which is known as the Baphomet mechanism, is one of the proposed processes, which is also observed to operate in the surface layers of the sun. We also have the classic mean field alpha effect, which arises out of helical turbulence. There have been alpha effects which have been proposed due to buoyancy instabilities. Even small scale dynamos can in principle produce a magnetic noise which can feed into both toroidal fields and poloidal fields, but I will not go into those details in today's talk. But it's important to keep in mind that there are in principle a variety of processes that can reproduce the poloidal field from the toroidal field. So the dynamo is essentially a process which recycles the poloidal component of the magnetic field to the toroidal component, and vice versa, mediated via different processes such as flux transfer processes such as meridional circulation, turbulent diffusion, turbulent pumping, which I may come to at some point in time in my talk. Okay. I am going to again primarily focus my talk on flux transport dynamos, because flux transport dynamos are the basis for the predictive dynamo models of the solar cycle that I'm going to be talking about. So what is the flux transport paradigm? The flux transport paradigm is this, that we are not really doing direct numerical simulations. We are not worried about the nonlinear feedback of the magnetic fields on the flows. We take the flows as given, as inputs, and we solve the induction equation. The constraints on the flows come from heliosseismic observations. The differential rotation is fairly well constrained. The meridional circulation is weakly constrained, but well constrained in the near surface layers, and we build to theoretical understanding and ideas of mass conservation, a profile of the Meridional circulation in the interior of the sun. There are some controversies about what kind of circulation it is, single cell or multiple cell. Typically, the flux transport dynamos assume a single cell Meridional circulation. On top of this, we have mechanisms inbuilt into this model which mimic the buoyant emergence of tilted bipolar magnetic regions. We inbuilt through parameterization the process that encapsulates the main field alpha effect. We can also encapsulate the impact of small scale dynamos through noise, which are all again parameterized. The flux transport processes then have been created with a variety of different source terms. For example, the Backward-Clayton mechanism, which alludes to the emergence of tilted bipolar transport pairs and the redistribution of their fluxes through the surface flux transport process. Flux transport dynamo models have also been built imbibing the essence of the mean field alpha effect, sometimes working in isolation or working together with the Backward-Clayton mechanism. And then we also parameterize the Meridional circulation, turbulent diffusion, turbulent pumping into these models. Okay, I want to drive home this point because this is fairly important. When you have a variety of sources proposed for the generation of the polar orbital field, the question that comes into mind is what is the dominant source term for the polar orbital field? And more importantly, what is the dominant source that is driving variability in the sun's polar orbital field, which then creates the variability in the toroidal field, which manifests as cycle to cycle variations in the sunspot number. Essentially, what you see here on the left is a cartoon depicting the Backward-Clayton paradigm, where you have this very systematic emergence of tilted bipolar sunspot pairs following the Joy's law, where the tilts of these active regions are larger as you go to higher latitudes of the sun away from the equator. Turbulent diffusion breaks apart this field and facilitates the cancellation of the leading polarities of these active regions across the equator. The remnant flux is carried both by diffusion as well as meridional circulation, which is poleward in the surface layers towards the polar regions, where it first destroys the field from that is remnant from the older cycle, and then builds up the new field for the current cycle. And that in turn recreates the large-scale dipolar field of the sun that manifests as the polar orbital field, which is then sheared by the omega effect or differential rotation to recreate the polar orbital field. You actually see this process in operation on the solar surface, where on the right-hand side here, where you see this emergence at low latitudes and the redistribution of the radial fields and their poleward transport, where they reverse the old polar field and then impart the new field, building up a large-scale dipole. Observations support this Backward-Clayton paradigm. There are theories which are purely analytical, which supports the Backward-Clayton paradigm. Data-driven models which imbibe the essence of the Backward-Clayton mechanism to recreate the polar field, and subsequently the dynamo coupling through the dynamo to recreate the toroidal field also supports this paradigm. So I think that there is enough observations and enough theoretical and modeling work to suggest that the Backward-Clayton mechanism is the dominant source for the polar orbital field that you observe on the sun. Well, the sunspot cycle doesn't look like this. There are variabilities from one cycle to another cycle. So the question that one needs to then ask is, what is at the basis of these fluctuations or variability that we see, that we observe from one cycle to another? And can we understand this processes at a level which can be reasonably approximated or parameterized in models to transform this understanding to predictive models? Well, so what is the origin of solar cycle fluctuations? I already talked about two kinds of alpha effect. There are many. The mean field alpha effect really results out of turbulent helical turbulence, and so you expect that there'll be fluctuations in the mean field alpha effect in the solar convection zone. For the back-to-Clinton mechanism, which involves the more coherent large-scale magnetic flux tubes which are rising to the convection zone, Coriolis force is fairly deterministic, which produces Joyce law. But you also observe a large scatter around the Joyce law tilt. And that arises, the current thinking is that this arises because of turbulent buffeting of helical flux ropes, of toroidal flux ropes, while they're rising to the convection zone, which imparts a sort of stochasticity around the mean tilt that is expected from the Joyce law. And the eventual result of that is that when you average this out of the tilt angle scatter of this individual bipoles, you get a mean dipole which varies from one cycle to another cycle. And this is at the basis of fluctuations in the back-to-Clinton mechanism, which acts as a source for the poloidal field. There are also nonlinearities in the sunspot cycle, which arises because of nonlinear interactions from either the Lorentz feedback of magnetic fields on plasma flows. There have been propositions that helicity quenching could play an important role as a nonlinear feedback mechanism. Time delay effects have been proposed and has been explored through various kind of modeling paradigms, including simplistic mathematical reduced dynamo models, which also act as a source of nonlinearity producing fluctuations in the sunspot cycle. The dynamical buoyancy effects, which we studied recently, which also gives rise to fluctuations in the sunspot cycle. There is also the issue of tilt quenching. When you have very strong magnetic fields, the Coriolis force tends to be ineffective on such strong magnetic flux tubes. And so the tilt angle gets quenched, and that also acts as a source of nonlinearity, particularly for the back-to-Clinton mechanism. And then this is not really a nonlinearity, but if you have the emergence of what has been termed as ROG active regions or highly anomalous active regions, which do not follow the Joyce law, like for example, antihelial regions contain a large amount of flux that can introduce severe perturbation into the poloidal source, thus acting as a source of variability in the sunspot cycle as well. It's not really a quenching mechanism because it can, in principle, log active regions could act both ways. One can have regions which follow Joyce law and have large amount of flux or tilt, which then will positively add to the poloidal field, or you can have an antihelial region, anti-Joy region, which really sort of acts as a mechanism which reduces the poloidal source drastically. Question and the problem, one of the challenges really is this: we don't really know how nonlinear is the solar cycle. Is this dynamical nonlinearities that have been proposed, are they important in the context of the solar cycle? This is a question open to debate. I have an answer to this question, but I'd rather not give this answer now. We can talk about it if people are still sort of, with me at the end of this talk, because that is going to open a whole can of worms. But I want to throw up this plot with this really nice diagram, which is a bifurcation diagram generated by Paul Charbonnet. So what you see here is a stochastically forced nonlinear dynamo, where the x-axis denotes the dynamo number, and the y-axis, the energy, is really the square of the amplitude of the cycles. So when you increase the forcing or increase the dynamo number, implying that you increase the magnitude of the source term relative to the dissipative term in the dynamo equations, you have this interesting behavior. First, you have singly periodic cycles, and then there is a period doubling bifurcation. And then you reach a sort of a state where the cycle can exist in two different states with two different periods. And as you keep on increasing the dynamo number, there is another period doubling bifurcation in these two branches. And finally, at very high dynamo numbers, the dynamo becomes completely irregular, perhaps hinting that you have hit the chaotic regime. The question is, where is the sun operating? There are views which claim that the sun is in a highly nonlinear regime, is a very highly chaotic dynamo, where you cannot make any predictions. So one of the papers which postulate this uses this kind of a plot to kind of justify this position, where you have this nonlinear dynamo mechanism, and you perform different simulations with slightly different initial conditions, and you see that the solutions diverge over a certain period of time, implying, or at least interpreted by this particular group to hint that you cannot make solar cycle predictions over long time scales. The question really that we would like to pose is this: is short-term predictions possible? And is this something that is new, or is this something that was known? If you go back to I talked about climate modeling and weather predictions. If you go back to the classic paper by Lorenz in 1963, this fact was in fact already recognized, that if you have a highly nonlinear system and you have slightly different initial conditions, or you have observations that are not exact or which are inaccurate, then even slight inaccuracies over a long period of time will lead to very divergent solutions, which might imply that long-term predictions are not possible. And this we sort of believe in. But in this context, the question that we would like to pose is this: is short-term prediction possible of the solar dynamo mechanism? And if yes, how long is the predictive window or predictive memory in the system, which allows you to predict over a certain time scale? So let's look at the alpha omega dynamo equations. And again, without getting into technicalities, I would like to break this system of equations into different the terms into different classes. There's some classes of terms, for example, the flux transport terms and the inductive term for the toroidal field, which is the omega effect term, which are fairly deterministic. However, the flux transport terms, which involve the meridional circulation, which involve turbulent pumping, which involve turbulent diffusion, magnetic buoyancy, are terms that are introducing certain delay in the systems, because it's transporting fields spatially within the convection zone of the sun from spatially segregated, within two spatially segregated source regions, particularly if you believe in the Backward-Clayton idea, where we think that the source is located in the near surface layers, whereas the shearing is happening throughout the convection zone, and these flux tubes are being stored at a layer which is stable to magnetic buoyancy. So this flux transport terms induce some delay or time delay in this process, which is akin to saying that you're introducing a dynamical memory in the system. The toroidal field source, which is the induction of the poloidal field to the toroidal field, is thought or known to be fairly deterministic. However, the poloidal source is where the fun is. this is a term which is known to be highly stochastic, because from theory you expect either the main field source or even the backward mechanism to have stochastic perturbations. This is also nonlinear, because nonlinear feedback mechanisms that I talked about do play an important role in quenching this term. Also, to some extent, this term as well. However, if you look at the torsional oscillations that are a manifestation of this feedback, torsional oscillation is a very small percentage of the differential rotation. So that feedback is small, but here you would expect both stochasticity as well as dynamical nonlinearities to play an important. So this is something that really breaks down the predictive link. However, the important thing here, which allows us to bypass this sort of uncertainty, is that you really are observing this term on the near surface layers. Why are you observing it? You are really observing the manifestation, the net effect of this source term in terms of the poloidal field, or at least the R component, the radial component of the poloidal field on the surface of the sun. So if you can actually get the surface observations, which is the R component of the poloidal field, and based on that, you reconstruct a global dipole and feed that back into the poloidal field here, which is acting as a source term for the toroidal field. You are really bypassing a lot of this uncertainty and reducing this system to a predictive system by utilizing these observations. And then your system of equations philosophically reduces to something like this, where you are predicting the evolution of the toroidal field given observed inputs of the poloidal field, imbibing the flux transport processes which involve some time delays, and then your dynamical memory, which is T0, really tells you how long into the future you can, is this memory preserved, and therefore how long into the future can you predict? And let's look at that question a little. Okay, so what are the important flux transport processes in the sun's convection zone? If you think of a spatially segregated source regions where the source term for the poloidal field is located in near surface layers, whereas the omega effect or the toroidal field source is in the somewhere in the convection zone, these two layers have to be coupled to this flux transport processes. So the poloidal field can be brought down into the convection zone through various processes like meridional circulation, turbulent pumping, turbulent diffusion as well. One of the slowest processes is meridional circulation, which takes about 20 years to couple this go through a cycle between the surface and the base of the convection zone. A turbulent diffusion, if you assume a typical value of 10 to the 12 centimeters square per second, which is a highly diffusive convection zone, then you have a coupling time of roughly on the order of 11 years to 14 years, which is on the time scale of the solar cycle. Turbulent pumping, our understanding of turbulent pumping is purely from direct numerical simulations. Suggests speeds of about 2 meters per second to even higher speeds, which would imply that the coupling would happen at much faster time scales of something of a fraction of the solar cycle. Now, what this implies is this. This implies that if you have a stochastic source on the surface layers for the poloidal field, the imprint of the stochasticity will be brought back down and manifest as a perturbation or variation in the toroidal field generation mechanism at the time scale of whichever of these processes is dominating this flux transport dynamics. Okay, so we explored this through this alpha omega dynamo models, utilizing stochastically forced, by which I mean the poloidal source was stochastically forced, and we also used nonlinear quenching of the poloidal source. So we had a stochastically forced nonlinear alpha omega dynamo model to explore propagation of memory from one cycle to another cycle in different kind of situations. So what you see here on the left is what we call an advection dominated convection zone, implying that the diffusion coefficient is very, very small, and the dominant time scale here really is the Maedler circulation time scale. So it's advection dominated, and we correlated the poloidal flux in the polar caps at a cycle, let's say n, at the end of a cycle n, with the toroidal field strengths of subsequent cycles. And what he found in this kind of simulation is that this correlation persists and is significant across multiple different cycles. Whereas if you assume a diffusivity on the order of 10 to the 12 centimeters squared per second, you are hitting the diffusion dominated convection zone. And there, the memory of the solar cycle lasts only over one cycle, implying that the poloidal flux, which is here denoted by phi r, is correlated only with the next toroidal, the next transport cycle, toroidal flux, the next transport cycle, phi dot n plus 1. The correlation lasts only over one cycle. The interesting thing is this: if you start off with the advection dominated model, and you introduce turbulent pumping into this model based on turbulent pumping profiles gleaned from direct numerical simulations performed by Kapila et al. Then what you see is this: the advection dominated models actually start behaving like a diffusion dominated model. And the reason really is you are short-circuiting the advective process of Maedler circulation, which is going through a whole loop by transporting flux directly between the upper layers and lower layers through turbulent pumping. And this reduces the memory again to just one cycle. So based on this, these simulations, we postulated that the dynamical memory, which allows predictions, lasts only over one sunspot cycle, wherein the poloidal field of sunspot cycle n predominantly influences the toroidal field of sunspot cycle that follows. So the poloidal field of cycle n would influence the toroidal field of cycle n plus 1 and not beyond. Subsequent to this theoretical analysis, Andreas and team at Harvard looked at the long-term series of polar faculty measurements, which was taken to be a proxy for the poloidal field of the sun, or the polar flux, and performed a correlation analysis very similar to what we had performed earlier with this theoretical dynamo simulations, where they correlated the average polar flux of cycle n with well, here that's with the toroidal flux of cycle n. This is the poloidal flux of cycle n with the toroidal flux of cycle n plus 1. This is with n plus 2. This is n plus 3. And they recover through these observations a very similar result, where they find that the poloidal flux at the end of a cycle n is correlated only with the toroidal flux of cycle n plus 1. And you see here that this all adds up nicely. And the reason that the poloidal flux of cycle n and the toroidal flux of cycle n are not correlated is because the poloidal source, which converts the toroidal field to the poloidal field, is stochastic, and that link is broken here. Whereas the conversion of the poloidal field of cycle n to the toroidal field of cycle n plus 1 is a deterministic, much more deterministic process, where this link is preserved, where if you know the poloidal field at the end of cycle 1, you have a very good handle on what the toroidal field cycle of cycle n plus 1 is going to be. And really this sort of implies that your predictive memory in sunspot cycles is short and predominantly lasts over one sunspot cycle, implying that you can only make predictions for the following cycle reliably and not beyond. So in principle then, what I've demonstrated to you is the theory of solar cycle predictability and memory, dynamical memory, agrees with what the observations throw up. Okay, having been confronted with this convergence, we pose this question to ourselves. Fine, this implies that sitting at solar minimum, you can in principle then predict the toroidal field of the next sunspot cycle. Is there a way where you can extend this window for predictability? Because this is something that all of us desire in the space weather community. The earlier you can predict what the amplitude of the next transport cycle is going to be, the better it is for mission planning, for estimating mission lifetime estimates, and stuff like that. So it has important implications for space weather and for planning of space missions, right? Okay, the answer to this question really existed in the sense that there is this whole other community of people who have been doing what is known as surface flux transport simulations. Okay, so what is surface flux transport simulations? The essence of surface flux transport simulations is that you essentially are solving the R component of the induction equation at the solar surface by incorporating the observed sunspot numbers or idealized magnetic bipoles whose statistics fit the observed statistics of sunspot cycles. And then you let this emerged magnetic fields evolve on the solar surface, mediated via surface plasma transport processes such as turbulent diffusion, supergranular diffusion, Meitner circulation. And that redistributes this surface fields, enables flux cancellation and the build-up of the polar fields. So if there is a way that you could incorporate a synthetic profile of the declining phase of sunspot cycles into the flux transport models and predict the poloidal field, and then use this predicted poloidal field as an input to the predictive dynamo model by coupling them, then we're increasing the predictive window by almost up to a solar cycle. This is enabled or facilitated by the fact that the declining phases of sunspot cycles appear to be similar, irrespective of what is the amplitude of the sunspot cycles. But there are certain pitfalls to this, like the emergence of ROG active regions or anomalous active regions, which one needs to be careful of or be cognizant of when utilizing this kind of a scheme. So what we do is we essentially follow this philosophy where we use a 2D kinematic dynamo model in a predictive mode to generate the toroidal fields, and a 2D surface class transport model which incorporates or assimilates the emergence of bipolar magnetic regions on the solar surface based on the observed statistics of tilt angle distribution and fluxes into this model. And then we recreate the poloidal field, and then the poloidal field is made to fit back at every cycle minima into the solar dynamo model. By doing this and avoiding continuous data assimilation, as was done by some other groups, we are also avoiding a certain problem that can creep in, where you can build in sort of a error into the system, which allows for predictability without really truly being a predictive model. And I'm not going to details of that, but I think some people who have worried about why the predictions of sunspot cycle 24, the physics-based predictions of sunspot cycle 24 diverge from each other, would be aware of this. All right. So what you see here is a century scale simulation of a surface flux transport model based on observed emergence statistics, where the bipoles are idealized bipoles which follow the observed statistics of tilt angle distributions of Joyce tilt angle distribution and fluxes. The thin lines on the background are the polar faculty observations, The solid curves are the simulations for the northern and southern hemisphere. And you see that we have more or less done well here in terms of reproducing the poloidal field or the polar field evolution, except this one cycle here, which is transport cycle 18, and I'll come back to that. Now, what we do is we do the simulations, and we perform this in 2016, 17, and we recreate the declining phase of transport cycle 24, and we built in a reasonable range of uncertainty through ensemble forecasts by varying the tilt angle, the flux, the emergence latitude, and we perform 140 different simulations, thereby creating a range of possibilities for the poloidal field at the end of transport cycle 24. Then what you do is we couple this into a predictive dynamo model where we are only solving for the toroidal component of the magnetic field by incorporating this poloidal field at every cycle minimum into the dynamo. And the result of that is this, which is one of the first coupled surface class transport plus dynamo model, which is data driven over century scale. The black curve here is the observed transport cycle time series. The red curve is the simulated transport cycle time series. So up to this point here, you can consider this to be hindcast. From then on, you can consider this to be the forecast for transport cycle 25. So we reproduce previous cycles well, except transport cycle 19. We don't quite clearly understand why we crap here for transport cycle 19, but this is something that is a challenge in the community to understand this discrepancy. Recall that transport cycle 19 was also the strongest cycle observed in the last 100 years. But we do fairly well otherwise in reproducing the other cycles. And our predictions of transport cycle 25 is that it's a cycle that is going to be similar to transport cycle 24. Our standard run, which is this middle curve here, is slightly stronger than transport cycle 24. The range of predictions, and I want to emphasize the range of predictions, because when you are building models which have certain parameterized terms, it has guesses for the declining phases of the previous cycle. You cannot escape ensemble forecasts. You have to build in uncertainties. So the range of uncertainties are just, takes the range of transport cycle 25 that we predict to be just slightly below transport cycle 24, which was 111 in terms of transport number, to something like 139, so somewhat stronger than transport cycle 25. Weak to moderate transport cycle 25 is what we predict. And we do not predict one single number. I want to again emphasize that this range is what is important, and we expect transport cycle 25 to be within this range. If anybody predicts a transport cycle as a perfect number and this miraculously agrees, that is pure chance. I think these predictive models have to be like ensemble predictions. And this is a point I want to drive home, because there are various uncertainties in the model, and if we don't honestly talk about it and talk about the range of predictability, then this field we are going to destroy. Okay. We are now in a position to go back, take a step back, and look at one half of our prediction, namely, how did our prediction for the polar field at the minimum of transport cycle 24, which happened in December 2019 or in 2022, how did that compare with observations? So, so proxy for the dipole moment is this dashed, thick black dashed curve, which is the polar flux in the north minus south by 2, which is from the Wilcox Solar Observatory, which is managed by Stanford Solar Group. This dark green line is our standard prediction. I do not know if Todd Hexima is in the audience, but while we were doing this work in 2017, I recall that we wrote to Todd saying that, Todd, something is going on. We are doing these runs. Our simulations don't agree with what you see. And Todd came back and told us, hold off. There are issues with, I think, something like dust or something on the lenses, and in the process of cleaning it. And they revised this. And I recall that after revision, at least that part agreed more with what we were doing. Anyway, right now we have the benefit of hindsight. We have the predicted polar field. We have the observed polar field, and I leave it up to you to judge how did the predictions go. This is the standard run. Again, I will insist that the standard run agrees, but don't take it for granted. What is important is the predicted range. Okay. How does our physics-based model forecast compare with other physical model-based forecasts? And there have been a few of this already, and these are highlighted out here. This dashed line is the amplitude of sunspot cycle 24, just for context, and these bars are the predicted amplitudes of sunspot cycle 25. And you see that within error bars, I repeat, within error bars, these predictions are consistent with each other. And I think that is a big step forward. As a community, I don't think we should worry about whose forecast, the standard run, turned out to be exactly right. I think what we should emphasize, and the point that we should drive home, is this, that this physics-based forecasts have now converged for sunspot cycle 25. Now, of course, there is a caveat. Caveat being, consensus does not necessarily imply that we are all right. It could also imply we are all wrong. But I would put that second possibility to be quite low at this point. Okay. Where do we stand? What progress have we made in the last decade or so in terms of solar cycle predictions? I would pose some questions and answer them, and that for me is progress. The first question is it possible to predict the solar cycle? And there is an unequivocal answer to that. The answer is yes. If yes, what is the best proxy for prediction? The best proxy, if you're using empirical forecasts, is the polar field or the polar flux. Everything else is not so good. If you have a proxy for the polar field or polar flux, that by default would also be a good predictor, but the polar field and the polar flux are the primary determinant of the amplitude of the next cycle. Now, do we understand why one dynamo-based forecast for cycle 24 diverged so significantly from the other forecast? The answer to that is yes, we do understand the differences, why they diverged, and that itself also is progress. What can we predict and how accurately can we predict? We can predict the amplitude of the following sunspot cycle. We can also predict its timing. The prediction of the timing is dependent on also the amplitude, because if you have a larger amplitude, it tends to peak earlier. If you have a lower amplitude, it tends to peak later. So the range of predictions that we actually showed here, if I just go back a couple of slides here, also has a range of timing associated with it. Our standard guess is somewhere late in 2024, based on the standard now. Okay, so let's now get back here. How accurately can you predict? That is an open question. I think the way to go forward is to build in this uncertainties, reasonable range of uncertainties in your parameters into the model and make ensemble forecasts, which is more realistic than predicting one number. Okay, how early can you predict? Certainly not before the previous maximum. You need to be at least at the maximum of the previous cycle to have an understanding of how the declining phase of the solar cycle is going to look like by creating synthetic profiles. And of course, the earlier you are from the minimum, the chances are that your accuracy is going to be lower because you might be hit with some highly anomalous regions. So certainly not before the previous maxima, but with some degree of confidence between the next maxima and the previous minima. So that's where we stand in terms of the progress that you've made. Okay, I want to now. I'm sort of getting close to the end of my talk. Let's see. Yeah. So how well placed are we to take this understanding from what we've gleaned from the solar cycle in addressing challenges that we face in understanding the activity of other stars? I want to highlight this one work that we did last year, which is based on assimilating all these ideas from this solar dynamo models we have been doing to construct a simplistic mathematical model to explore the interplay of stochasticity and nonlinear dynamics and magnetic noise in terms of explaining a diversity of phenomena. And I would encourage you to read this paper, which self-consistently explains why the gyrocronology relations break down at about the solar age for a sun-like star. It also explains why the sun is relatively inactive compared to other solar-like stars. And it also explains why you see a bimodal distribution in the long-term reconstructed sunspot time series, which is a work that Ilya Ususkin and Sami Solanki have been doing for a while. I would encourage you to go and read up this paper, which imbibes a lot of the physics that we have discussed and can explain a diversity of phenomena in the context of stellar activity. Okay, I will skip this concluding remarks by just quickly summarizing it and saying that in spite of early debacles for solar cycle 24, in the intervening decade, we have made some profound progress in understanding the predictability of solar cycles. And we are now at a stage where at least the physical model-based forecasts for solar cycle 25 have converged to indicate that we are going to have a weak to moderate solar cycle, similar or slightly stronger than solar cycle 24, with certainly no indication of the sun sliding into a model-like minima, which was what was being widely speculated before this physics-based prediction started coming. I want to end also with some challenges and opportunities. Kind of models that I talked about are alpha omega kinematic dynamo models. I really did not at all allude to direct numerical simulations. However, this backproclaton mechanism, which seems to be really at the basis of explaining this decadal scale variability and succeeds in hindcasting the solar cycles, previous solar cycles so beautifully, is not very well manifested in this direct numerical simulations. We are starting to see coherent wreaths of flux tubes, which tend to rise and give rise to what looks like ordered preferential sort of latitudes of emergence of sunspots, but we still don't get the systematic tilted bipolar magnetic regions that we see in the sun, and which is the basis of the backproclaton mechanism in this DNS models. So this is one of the challenges that I think is going to drive the field in the near future, where we would like to see the backplacking mechanism manifest in this direct numerical simulations. Now, another profound question is the sun really a flux tube flux transport dynamo? This is a question that Manfred Schuster looked at very early on, and then there has been absolutely no attention to this. And this is something that might be what looking at as well. Okay. The other question is this: if the polar field is the primary determinant of the toroidal field of the next cycle, and thus the sunspot cycle amplitude, do you need dynamo models at all? I mean, you can just be making polar field observations and making these predictions. That's a very important question that the dynamo community needs to worry about. Well, the observational challenge is this. It's very clear to us now that the backplacking mechanism, the near surface dynamics leading to the destruction and the rebuilding of the polar fields at the high latitudes of the sun near the polar regions, which can be constrained by polar flux measurements, and in the strength of the polar field, plays a very significant and fundamental role in governing the amplitude of the next sunspot cycle. However, if you're sitting in the plane of the ecliptic at the Earth, and you have magnetographs on Earth, you have magnetographs in missions, space missions, which are at L1 or which are low Earth orbiting missions, you are really stuck in the plane of ecliptic, and you are not really making a very good estimate of the polar fields because of high projection effects. This is how the poles would look like if you could have a mission which flies over the poles. Solar orbiter is going to go up, I think, 30 degrees over the ecliptic. But that's still not enough. So the sun's poles are still to be unveiled and remains as one of the last great frontiers of solar physics. And a polar field mission would certainly return transformative information, not just relevant for dynamo theory, not just relevant for predicting the next sunspot cycle, but also to look at the polar field landscape, which would be very different from what we are seeing from near ecliptic observations. So this is another opportunity that exists in front of us. So with that, I think I'll end, and thank you very much for your attention.
Thank you for the very informative and detailed introduction. We are a little bit over the time, so Nick he says in the chat that he has quite many questions, but he has to leave because he has some other meeting. But let's still have a few questions. Do people want to ask any question directly? You can speak up directly or raise your hand. Gustavo?
Hi. Dibyendu, thank you very much for your talk. I have still a question about the Babcock-Layton mechanism, because I agree that this diffusion process that is the Babcock-Layton process happening at the surface, it's observable. But in the induction equations that you use for verify for how long can you predict the cycle, you use a term that is an alpha term. But if it is a Babcock-Layton mechanism, it doesn't have any mathematical foundation. So there is no closure that can take you to that term. So this is kind of a this is alpha.
Right.
If you have if you have turbulent alpha, these turbulent alpha effects, they come from a closure to a turbulent closure. But for a Babcock-Layton term, there is nothing like this.
Okay. So yeah. So I get your question. Okay. So fine. So you're saying that you can attain closure to the main field treatment, but at what order? And is this something you have to truncate? You are truncating at some order. Is that realistic? Is one question that you have. But let me finish. We are not really using the Backlund mechanism in terms of an alpha effect in the predictive models. What we're really doing is we are utilizing the surface flux transport model to recreate the surface field. And from the distribution of the radial field on the surface, we reconstruct a dipole moment, which is then fed into this equation. So we are really completely bypassing this. We are not dealing with a mean field alpha effect in the predictive models in the flux transport dynamo that you use for prediction.
Yeah, it's a 2D mean field transport model, right? So,
so
in
it
that
has
case,
nothing to do with, so in principle, I mean,
so
mathematically comes really from the surface flux transport. Driving really comes from the input from the surface flux transport.
So you put this term basically because it's observed, but mathematically these equations, these equations are not mathematically correct. Do you agree with that?
I will differ from I'll differ from you on that point, and I will say that it's a source term that that is not attaining closure from the classical traditional idea of the mean field alpha effect that you have in mind. The Backlund alpha effect does not, I mean, I'll not even call it alpha effect. The Backlund mechanism does not arise from any kind of averaging over small scale terms. The Backlund mechanism arises from the emergence of a tilted omega loop. And that is the problem that I alluded to as a challenge and opportunity at the end of my slide, is how to manifest that in direct numerical simulations. If the direct numerical simulations are not producing a coherent toroidal flux tube which is rising up and giving rise to a net dipole, then that's a problem that needs to be addressed. And I think therein is the opportunity. How do we emerge this Backlund scenario in the direct numerical simulations with all the scales from small scales to the large scales, the sunspots incorporated in the model? I think that is a challenge that is really going to drive the field forward.
Yeah, but it could be a side effect.
I don't believe that. I think it is the dominant mechanism which is driving the.
But you say that it doesn't come from a closure, but it should come mathematically from somewhere.
Well,
because it has to be MHD. Otherwise, we are.
I agree. But if you cannot encapsulate the buoyant emergence of tilted bipolar active regions in your MHD model, it's finally a model, right? Then you are far from the truth, right? You can have beauty in mathematics, but if you're not capturing reality, you're not getting anywhere. You have built a mathematical model which is pretty useless. It doesn't reflect.
Or vice versa.
Well, I mean, these models are being useful, right? It's being utilized for predictions. It's helped us reconstruct century scale activity, and we'll wait and see if something that we predicted back into, the predictive runs were completed in 2017, not but just us, but various other groups, whether those actually agree with with what happens in reality, right? I'm a strong believer in observations.
No, of course, I believe in observation, but I believe too in mathematics.
Yeah, sure, but I don't believe in the beauty of mathematics over observations. Let me be very clear on that.
Yeah, I agree. It's kind of let's say that's a phenomenological term.
But it's a problem, and this problem needs to be addressed and solved. And this is why I said that we have an opportunity there in addressing that.
Yeah, with that I agree. Yeah. But that's a phenomenological term. Let's have
absolutely.
This
yes, this is a phenomenological term. Absolutely.
Okay.
Thanks, Gustavo. I love these conversations with you.
Thank you.
Yeah.
I see Alfio and Rick with hands raised. Alfio, you first. You are muted. We don't hear you.
Yes, okay. Thank you for this nice talk, for this nice overview of the problem. The point I would like to make is that I am a little bit confused, going back to the question that Gustavo raised, because by reading the abstract of your talk, it is explicitly written that it is a Babcock-Lighton model, which is at the core of your prediction. Now we are telling that it's not a Babcock-Lighton, so I am a little bit confused. My problem...
I am a little bit confused because I said that the Babcock-Lighton model is what is at the basis of the prediction. The Babcock-Lighton mechanism is what is driving the variability.
Well, there is something which I really don't understand, how the way the Babcock-Lighton model enters in your prediction. My experience is the following, that every time I try to put the source there near the surface, in any dynamo model of the sun, I get the quadrupolar solution are much more easily excited. And I'm sure you know.
Absolutely, absolutely. And you are possibly working in the advection dominated regime.
At the moment, I am absolutely convinced that if you do this, you are in big troubles with the global parity of the solution that you had to face. So I'm sorry, I'm absolutely not convinced that can be, even if you can make prediction. I mean, you can make prediction, but the model, you cannot ignore that there is at the core of the model that this is still big issues that has not been solved.
The parity issue has been.
I am really very much.
I've got your question. Can you please allow me to answer it? You have raised a question about parity.
Yes.
Parity question has been
about the parity. Yes, that's right.
Yes. Parity question. I just send me an email. The parity question has been thought out and finished. You are perhaps working in the advection dominated regime. If you work in the diffusion dominated regime, the two hemispheres are well coupled and you tend to stay in the dipolar parity state for much longer periods of time. We have written a recent paper, I think this was in 2020 or 2029, parity shifts over very long time scales, even in diffusion.
A very strange diffusion profile near the bottom, the convection zone, very unnatural one. So I don't think that.
I don't understand.
I don't think that solves the problem. You are dominated by diffusion in that case.
Yes.
So,
you are not at the base of the convection zone, in the convection zone.
The problem is still there. I want to be honest and tell, well, we still have the problem with that.
I didn't quite understand what you mean by unnatural diffusion at the base of the convection zone. You don't even know what diffusion coefficient we use, do you? The strong diffusion is in the convection zone. In the base of the convection zone, nobody uses a strong diffusion, right, in these models, because it's well understood that the radiative interior, the tachocline, is not strongly diffusive. So the diffusion coefficient there is much smaller, right? So when I say diffusion dominated convection zone, I imply the diffusion is strong in the convection zone, not at the base of the convection zone. And the diffusion coefficient that one uses is typically something that arises out of mixing length theory.
Yeah, perhaps at the radiative zone is not sufficiently small. It's
yeah, so we don't really go down. So we go down to something like 0.6 solar radius, and there the diffusion coefficient that we take is typically on the order of something like 10 to the power 8 centimeters square per second. You can go even smaller.
There is a gradient of what?
Sorry?
10 to the 2 or 10 to the 3 in the diffusion coefficient in the transition?
In the transition, so the transition happens from 10 to the power 12 to 10 to the power 8. The stronger transition you have, the stronger. So there is this 1 by eta del, del eta del term, right? The stronger flows you will drive down, and that also has an impact in the sense that it kind of pushes down the fields that you see in the convection zone into the radiative interior, which can sometimes be a problem if you have very strong gradients.
It is a problem.
Okay. Last question. No, last hands raised, Rick.
Yeah, I have a kind of a naive question, maybe. You mentioned that your modeling shows that we're not sliding into a moderate minimum, which I think there's no question about. But I'm kind of curious, would it be possible for you to run your modeling in reverse to say, if we had a moderate minimum, what would be the previous conditions in the previous cycle that could lead to that? And so, in effect, how many solar cycles do you need to, would you in theory need to be able to predict when we would go into a moderate minimum?
Yeah, so this is a very good question, and this question has bothered me for quite a while. I mean, if I rephrase your question somewhat, is can we predict when we are going to enter a moderate minima? This is one of the papers that really looked at this, and again, I encourage you to look at this paper. This is quite a detailed paper looking at the nonlinear dynamics of the solar cycle. Okay, so we have been doing simulations to understand. Is there a threshold in the polar field, which is indicative that you are going to hit a moderate minimum? We have not yet arrived at a consistent answer to this. We have not even arrived at a consistent answer or a physically, I would say, physically consistent answer at what could in principle drive the sun into a moderate minimum, other than this rather simplistic notion that if you have multiple stochastic perturbations all sort of working in the same direction, adding to a negative feedback on the source term for the polaroidal field, you will get into a moderate minimum. And that's what this paper says. But what is the source of those, whether it's anomalous active regions, whether it's magnetic noise, is open to question. And the other question that is related to this is this, that when you're talking of moderate minima and long-term modulation, the nonlinear feedback mechanisms play an important role, or so it is believed. So the question then is, in fact, if the nonlinearity is not very significant in the model, could stochastic perturbations alone generate the supercycles that we see and grand maxima and grand minima episodes? This question is not yet consistently answered. We don't have an answer to that. So to summarize my answer in one line, I think we understand decadal scale variability at this point in time better than we understand long-term solar activity fluctuations and supercycles.
Thank you.
Shay asked a question in the chat, and then Robert has raised hand. Shay, do you want to repeat your question?
Sure. I was just going to say, in terms of sort of the debate that we had going on with Gustavo and Alfio and Dibyendu, sorry, I'm mispronouncing your name. It seems like that would be a sort of a fun thing to do in some sort of a future workshop, in a shine type discussion where we kind of bring two sides of an argument and hash it out in a room together. I don't know if anyone else would be interested in that. But
where are you doing this?
I don't have it planned yet.
Gustavo offering a beach in Brazil. I am all up for it.
All right, we'll have Gustavo plan it then.
I mean, this is something that is fundamental. There was a workshop in Bern. We discussed this as well. I think these two communities have really worked like tangent to each other, and we never really have converged. But I don't think we can solve this question in one workshop, but I think the seeds of this have to be planted. And this is something that is crucial for progress in dynamo theory and convergence across this group of people who use, like me, who use more predictive, data-driven, parameterized models, and those who use direct numerical simulations. I think we need to arrive at some sort of convergence by working together and trying to imbibe the essence of what is observed, what is manifested as a backpacking mechanism in the direct numerical simulations.
Yeah, so baristas, keep that in mind for something in the future.
Yeah, sure. I would be very happy if somebody takes the lead, and I'm happy to, work out a program with Gustav and others on this. I think it'll be fantastic.
Okay. Last question from Robert. So it's very late at speaker's time zone.
If you're worried about me, I'm good. I mean,
okay, thank you.
People who want to leave can leave. People who want to stay and discuss, I'm happy to be here and discuss.
Okay. Okay. So you will have a question from Robert.
Yes, I was just a little bit surprised that you don't think we understand the long-term variability, because for me, it's, I think, clear we won't get sunspots unless we produce toroidal fields of 10 to 20 Gauss or more, and the fluctuations we see in the alpha effect, or at least in the tilt angle of sunspots, this completely accounts for all the variability we see from the cosmogenic isotopes. And there's a paper by Manfred and I on this, I think, in 2018. So I'm a little bit surprised there.
Do you think we understand supercycles? What is at the basis of supercycles?
I think all the observed variations we see from cosmogenic isotopes, from direct observations of sunspots, are consistent with random noise from the scatter of the joy
Yeah,
soul.
so this paper as well, right? In the sense that, but at a very simplistic level, right? I mean, remember that.
No, I don't think it's a simplistic level at all. I think.
So you think?
Yeah,
but can we answer this question? Can we answer this question that okay, at a predictive level, what we're doing with this kind of models, including this paper, is a qualitative level, right?
No. So Manfred and I, you put in the level of noise implied by the variation in joy sort, the scatter in joy sort, and you reproduce the statistics of Maunder minimum-like events. You reproduce the power spectra for the data over the last 10,000 years, over the 400 years of sunspot records. So I'm
aware of those papers. But my point was that yes, we understand the statistics. Yes, the distribution functions. Yes, but are we at a level where you can predict what is whether there's going to be a super cycle, grand maxima, or a grand minima next? I don't think the understanding.
I think the point is at a level of 2-3 sigma, you can have grand minima, and this is just from the facts that cycles vary about 40% from cycle to cycle. This variation you can trace back to the variation in the scatter and joy sort. So I don't see anything beyond this.
Okay, I mean, with that, I would tend to agree that you can perhaps predict a grand max, minima if your polar field threshold falls below some level. But I still don't feel that we are at a point where we can predict a super cycle sort of thing coming in. I don't think we can do that, but I think I agree with you that at the level of basic physics, qualitatively, we think we know what's going on here. In terms of what is driving it. And I think magnetic noise and stochastic perturbations can do the job. How important is nonlinearity? And this is, I think this will open a whole can of worms again.
So the nonlinearity, I should also point out, there's very nice work by Bidya and Akash on the latitudinal quenching.
Yes, but how important is nonlinearity in terms of the super cycles or long-term modulation, I think is an open question. What is your feeling? Do you think that long-term nonlinearity plays a role in long-term modulation?
And I guess not. I think the nonlinearity is probably this latitudinal quenching. Okay. And so I encourage you to investigate that a little bit more. That's very cute. But very nice talk. Thank you.
Thank you, Robert. Good discussing with you as always. Say hi to
Okay.
Shwangita.
Will
Okay.
do.
Sorry. I was always trying to interrupt. Okay, so no other hands raised, but Todd and Alfie had comments in the chat. But Alfie probably have to leave because he has had to leave.
I can read them. Where is Todd? I don't see.
I was just saying thank you for underscoring the importance of the polar field measurements. You know, I think it's something that we've tried to do from Earth for a long time, but really going to higher latitudes is what we need to do to get a little bit more definitive thing. Both for the fact that the polar fields are interesting, but also to look at the convection and how things change at high latitudes, which, you know, may be a bridge between what you're doing and what Gustavo and the others are doing in that way. The other thing was, you know, I'm always interested in differences between North and South. You know, had the two cycles, the northern cycle and the southern cycle, had the same phase in cycle 24, we would have had a much higher peak.
Yeah.
And, you know, there's often this difference between the North and the South, and, you know, sometimes one leads and sometimes the other leads. But, you know, tying these two things together and trying to understand how they interplay, I think is really important, and another area where we can probably make some progress in the future.
Yeah, absolutely. I mean, I didn't talk about asymmetry at all, the difference between North and South. So I think Prantika, I don't know whether Prantika is here. She's in Durham right now and working with Anthony. She has looked at the asymmetry in the polar fields and how they impact the asymmetry of the next transport cycle. And it does play, you know, the polar field asymmetry seems to play an important role in determining transport cycle asymmetry as well. I do agree that that polar, you know, having out of ecliptic observations of the polar field is important. There's something else I didn't at all touch upon, which is the existence of these kilogauss flux tubes and their origin and what role do they have to play, if any, in the dynamo mechanism. Which is, you know, Hinode has shown that there are this kilogauss unipolar flux patches in the polar regions, whereas in the surface flux transport models, we are generally producing this very uniform, like average 10 Gauss magnetic fields. Whether it makes a difference or not is something that is still, I think, an open question. And I think observing them is going to have some important feedback on how we are thinking about the structure of the polar fields and on how they are inducted back into the toroidal field. So this, I think, is also something that one has to keep in mind, that I completely ignored the kilogauss flux passage that is observed on the solar surface, which at high latitudes, which none of us talk about usually.
Well, thank you, Dibyendu. I think that there's, you know, COFFIES can play a role in the next couple of years in getting us all together to talk some more. So I'm really interested about it. So thank you very much for the excellent talk.
Thank you very much for hosting me.
Okay, thank you for attending the talk, especially to our speaker for this very informative talk and this long discussion. Thank you so much, and hope you have a good rest at this time. Yeah, we really appreciate you coordinating this time with us at this time.
Thank you. I look forward to meeting you folks more often and getting involved. Many of my students and colleagues are already in there, and I'm pretty happy to see this crowd and to connect with them. Take care, everybody.
Okay.
Bye.
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 Thank you.
Bye.
Bye.
Bye-bye.
Bye.
Bye, Dibyendu. Thank you.
Bye. Bye-bye. Bye.